Hello friends, welcome back to my YouTube channel. In this video lecture, I'll be continuing my discussion on liquid extraction. This is part number 8 of the discussion, and today I'll talk about stage-wise liquid extraction. And in coming few videos, I'll be talking more about stage-wise liquid extraction. In this particular video, I'm going to discuss single-stage liquid extraction. So, you'll come to know how to take total material balance for single stage liquid extraction, then how to take material balance for the solute, then how to represent the operation on the equilibrium diagrams, ternary equilibrium diagrams. I'm going to discuss how to represent it on equilateral triangular coordinates and then the rectangular coordinates. I have already discussed those coordinates in my earlier videos. I'm giving link to the playlist in which you'll find all my videos on liquid extraction. The link is available in the description section. So, aim for today is to understand single stage liquid extraction. So, let us begin the discussion. Stage-wise contact or stage-wise liquid extraction. In order to carry out stage-wise liquid extraction, we need to contact the two insoluble phases in a stage-wise manner. So, stage-wise liquid extraction, it is carried out in stage-wise contact equipment, where the two insoluble phases, they are contacted in stages. In such equipment, in each stage, there is a provision, or there should be a provision, first to intimately mix the feed solution with the solvent, and after intimately mixing, the resulting mixture is allowed to settle, and after settling in the mixture will be settling into two phases, and we need to separate those two phases. So there should be a provision for physical separation of the two phases. Which two phases? Extract and raffinate phases. So each stage in the stage-wise contact equipment should have provision for intimately mixing the two phases and physically separating after the mixture separates into two phases, extract and raffinate phases. There should be a provision for physically separating those two phases. Each stage, therefore, since two tasks are to be carried out, intimate mixing and physical separation. That is why each stage, it is constituted of a mixer and a settler. So, mixer will be mixing the two phases, and after they settle into two layers, the settler, the mixture will be settling into two layers in the settler. So, mixer plus settler forms one stage in liquid extraction. So, we can understand that schematically. With the help of this schematic diagram, you have a mixer where there is provision of mixing the two phases, and then the mixture is transferred to the settler where it will settle into two phases, extract and raffinate phases, and they will be physically separated from each other after that. Okay, so this two equipment, they form a single stage. So when the feed solution, which consists of A and C, where C is the solute. So when the feed solution, it is transferred to the stage, it will first go to the mixture where it will be mixed with the solvent. After intimate mixing, the resulting mixture will be transferred to the settler. It will settle into two layers. The extract layer will be separated, and then the raffinate layer will be separated. The raffinate layer will be separated and the extract layer will be separated. So in this case, in stage-wise contact, in each stage, you have a mixer and then you have a settler. In mixer, the two insoluble phases are intimately mixed, and in settler, the mixture is allowed to settle into two phases, raffinate and extract phase, and then they are physically separated. So in each stage, you have those two equipment, mixer and settler, a combination of mixer and settler. Okay, so I hope it is clear to you. When I say a stage, in the case of stage-wise liquid extraction, there is a provision for mixing the two insoluble phases and separating the extract and raffinate phases, raffinate and extract phases after they are settled. Okay, now let us talk about single stage extraction, single stage liquid extraction. For our discussion, the ternary system consists of three components, A, B, and C. Three components in the ternary mixture: component A, component B, component C. Then out of this, C is soluble in both A and B, and A and B, they are soluble in each other, but only to a limited extent. So we are considering the scenario which is very common in liquid extraction. C is soluble in both A and B, whereas A and B, they are soluble in each other, but they are soluble only to a limited extent. Then the feed solution, it is composed of A and C, two components, A and C. And out of this, C is the solute to be recovered. Our aim in this single stage liquid extraction is to get separate C from the feed solution. Then the solvent used, it is B if you use pure solvent. Fresh solvent, if fresh solvent is used, then it will be just B. But if you are using a recovered solvent, then it will be containing all the three, the phase, solvent phase you can call in this case, it will be containing all the three components. B will be the major component, little amount of C and little amount of A will also be present if it is a recovered solvent. Recovered solvent, that means, well, let me just tell you. So you have used, let us say, a fresh solvent in an operation, and you have obtained raffinate and extract phases, and then this extract phases, the extract phase is then we need to recover solvent from the extract phase. For that, we need to use some other mass transfer operation. And as we understood previously, the most common mass transfer operation that is used for solvent recovery is distillation. So when you are recovering solvent from the extract phase, it will be containing all the three components. Majorly, it will be containing B, whereas there will be little amounts of C and A. And when this is true, when you are using a recovered solvent. If you are using fresh solvent, then there will be only B in it. So you need to understand this point, whether you are using a fresh solvent or whether you are using a recovered solvent. So if it is a recovered solvent, then all the three components will be there. Majorly, there will be B, and little amounts of C and A will also be present in that solvent. So in that case, we can call it as solvent phase, because it is containing B plus C plus A. Okay, so this is the solvent. And the feed solution and the solvent, they are contacted with each other in a single stage. Since we are talking about single stage operation, there is only one stage, and in that stage, the two solutions, feed solution and the solvent, they are contacted with each other. Okay, so this is how it is carried out. The operation, it could be carried out batch wise, or you can carry out in a continuous manner. The single stage liquid extraction operation, it could be batch wise or it could be continuous. Okay, now let us show or let us represent the single stage liquid extraction operation schematically. Let this circle represent the single stage that we are talking about. So I'm calling it as stage 1. So feed is admitted into the stage. Feed is solution of A plus C, and we are going to identify it by using two parameters, F and XF. I will shortly tell you what are those. Then this is contacted with solvent. Here I am showing I'm using a recovered solvent which will be containing all the three components, majorly B, little amount of C, and little amount of E. And this solvent phase will be identified by these two parameters, S1 and YS. I'll tell you what are this. Then you'll be getting raffinate, which will be containing again all the three components, A plus C plus B. And then you'll be getting extract, which will be containing again B plus C plus E. So measure is B in the extract phase, and in the raffinate phase, the measure component is E. Now the notations that we are going to use, F, it is mass if it is batch wise, or mass flow rate if it is a continuous operation. So F represents mass or mass flow rate of the feed solution. Then XF, it represents weight fraction of C, weight fraction of the solute in the feed solution. S1, it represents mass if it is a batch operation, or mass flow rate of the solvent phase if it is a continuous operation. Then YS represent weight fraction of C in the solvent. It will come into picture if you are using a recovered solvent. Then R1 is mass or mass flow rate of the raffinate phase, mass if it is a batch operation, mass flow rate if it is a continuous operation. And then X1 is weight fraction of C in the raffinate phase. And finally you have E1, which is mass or mass flow rate of the extract phase, and Y1 is weight fraction of the solute C in the extract phase. So these are the notations that I'll be using in my discussion. So if it is a batch operation, we'll be having masses of feed, solvent, extract and raffinate phases. And if it is a continuous operation, it will be mass flow rates. We'll have to deal with mass flow rates. Okay, so let us use this notation and understand how to write material balance for this operation. How to write the total material balance, and then how to write the component material balance or the solute material balance. Okay, so again for our reference, I have taken the schematic diagram. What happens when the feed solution is mixed with the solvent in this stage? Initially, it will be forming a mixture. It produces a mixture. And when this mixture is allowed to settle, it will settle into raffinate and extract phases. So when the feed solution is mixed with the solvent, it will first produce a mixture. And when this mixture is allowed to settle, it will separate into extract and raffinate phases. When allowed to settle, the mixture separates into extract and raffinate phases. Now let us talk about the total material balance, steady state total material balance, where we are ignoring accumulation. Okay, so the input is equal to output. The steady state total material balance will be F plus S1. You are mixing feed with solvent. You'll get a mixture, and then when this mixture is allowed to settle, it will separate into extract and raffinate phases. That's why the total material balance will be F plus S1 is equal to M1, mass or mass flow rate of the mixture, that is equal to E1 plus R1, mass or mass flow rates, depending on whether it is a batch wise operation or a continuous operation. So that let me call it as equation number 1. In equation number 1, as I said just now, M1 is mass or mass flow rate of the mixture that is formed when you mix feed solution with the solvent. So I can write two equations from this. One is F plus S1 is equal to M1. Let me call it as equation number 2. And then you have R1 plus E1, that is equal to M1. And I'm calling it as equation number 3. The total material balance by taking total material balance, steady state total material balance, I am getting 3 equations. Okay, so next we are going to write material balance for solute C. So it will be F into XF plus S1 into YS, that is total feed into weight fraction of solute in it, plus total solvent into weight fraction of solute in it, that is equal to M1 total mixture into XM1. XM1 is weight fraction of C in the mixture. So that will be equal to solute in the raffinate, which is given as R1X1, total raffinate into weight fraction of solute in it, plus solute in the extract, total extract into weight fraction of the extract and a weight fraction of the solute in the extract. So in this case, XM1 is weight fraction of C in the mixture. So from equation 4, I can write this equation Fxf plus S1Ys, that is equal to M1 into XM1, that is XM1 is equal to F into XF plus S1 into Ys divided by M1. And previously we got equation 2, which gave M1 as F plus S1, and now I'm going to use this over here. So it will be XM1, that is equal to Fxf plus F into XF plus S1 into Ys divided by F plus S1, and now I'm calling it as equation number 5. Okay, so let us continue. Now let us follow this on the ternary equilibrium diagram. First, we will follow it on the equilateral triangular coordinates. So let me first show the coordinates. So you have the equilateral triangle. This apex is representing pure A, this apex is representing pure B, and this one is representing pure C. And then you have the binodal solubility curve. Now we are going to follow the single stage liquid extraction operation on this ternary equilibrium diagram. First, we have to locate point F, and for locating point F, we are going to use the value of XF, which will be known to us. So by using XF, since feed contains A and C, point F will be located. The point F is going to represent feed solution on the diagram, and since it contains A and C, feed is A plus C. So that's why point F will be lying on the side AC, as the feed solution is containing just A and C in it, and point F represents the feed solution. Therefore, point F will be lying on the side AC. So I will locate point F with the help of XF. Then I will have to locate point S. Point S will be located based on the value of Ys. So whatever is the value of Ys, I can use that value to locate point S, and it will be located over here. It will be located close to the apex B, as the measure component in the solvent will be D. And if you are using pure solvent, let me first talk about it. If you are using pure solvent, this point will be lying at the apex. In that case, it will be containing pure B, and that's why S will be located at the apex B. Okay. So whatever may be the case, after locating F and S, the next task is to connect F and S. So you are going to connect F and S. Then we have to locate point M1. And for locating point M1, we are going to use the value of XM1. XM1, knowing we know how to calculate the value of XM1. XM1, we had got equation for XM1 previously. Using that equation, first get the value of XM1 and then use that value to locate point M1. First thing is, since F and S forms the mixture, point M1 will be lying on the line that connects F and S. So point M1 may be lying over here, point M1. So how are you going to locate it? You are going to locate it by using the value of xm1. Okay, so that is the case. Then the mixture, when it is allowed to settle, it will be settling into raffinate and extract phases, and they will come to equilibrium. So that means M1 should also lie on a tie line. M1 also lies on a tie line, and the end points of this tie line. So M1 should also lie on a tie line, and the end points of this tie line, what they will represent? They will represent the raffinate and extract phases that are formed at the end of the operation. So we are going to represent those phases by point R1 and E1 on this diagram. So this will be representing, this point will be R1, it will be representing raffinate phase, and this point will be E1, it will be representing the extract phase. So this is how you have to follow the single stage liquid extraction operation on equilateral triangular coordinates on the equilibrium diagram. I have discussed in details how to do all this on the rectangular coordinates. We will understand that shortly. Now I hope this is clear to you, how to follow the single stage liquid extraction operation on equilateral triangular coordinates, or Turner equilibrium diagram on equilateral triangular coordinates. Let us move ahead. Now let us talk about the Turner equilibrium diagram, which is drawn on rectangular coordinates. So for that, we will be plotting nx and ny. I will tell you what are this on the x-axis, and x and y on the y-axis. So in this case, nx, it is weight fraction of B in the raffinate phase. Ny is weight fraction of B in the extract phase. X is weight fraction of C in the raffinate phase. Y is weight fraction of C in the extract phase. And what are you going to do? You are going to plot nx versus x. Nx is plotted against corresponding x values, and when you do that, you get one part of the binodal solidity curve, the A reach part of the binodal solubility curve. And then you also plot ny against y. So ny is plotted on the x-axis and y is plotted on the y-axis. And when you do that, you are going to get the other part of the binodal solubility curve. So we are trying to understand, or we are trying to follow the single stage liquid extraction operation on Turner equilibrium diagram with rectangular coordinates. Turner equilibrium diagram on rectangular coordinates. So first, we have understood how to plot the binodal solubility curve. So you are plotting weight fractions of B in the raffinate and extract phases against weight fraction of C in the raffinate and extract phases. Okay, so I hope this is clear to you. If you have any doubts, so please let me know. Let us move ahead. Now, let us learn how to locate point here. We understood it, how to locate it on the triangular coordinates, equilateral triangular coordinates. Now let us understand how to locate point F over here. So for point F is located at a point which has coordinates of 0 and XL. That is, point F will be located on the y-axis because x coordinate is 0. So this will be the point. The point will be at x is equal to xf, and we are going to call that point as point F. And then after that, we need to locate point S. So point S, for locating point S will be located at a point which has this coordinates NYS and YS. What is NYS? Let me tell you. NYS is weight fraction of B in the solvent phase, initial solvent phase. And ys, as you know, it is so nys, let us first represent that point. Nys, as I said, it is weight fraction of B in the solvent phase. So it will be located over here, ys. And then I'll go to the, I'll draw a horizontal line because I need to locate ys also. So ys will be located somewhere here. And then when the two horizontal and vertical line meets, I'll be getting a point. That point will represent yes. That point will be yes, which is representing the solvent phase. And this will be true if you are using a recovered solvent. If you are using fresh solvent or if you are using pure solvent, then ys will be 0 and all that is there in the solvent will be B. That is, weight fraction of B in that case will be equal to 1. That is, nys is equal to 1. So, yes will then be located at 1, 0. So, it will be located on the x-axis where nys is equal to 1. So, in that case, s will be located over here. Right now, point S is located for the case where we are using recovered solvent. Now, we will be connecting F and S because connecting F and S indicates that you are mixing F and S to produce the mixture. So, let us connect points F and S and we have this diagram. Okay, so let us continue further. Now, we need to locate point M1. For locating point M1, we are going to use this coordinate. So, point M1 will be located at a point which has coordinates of n M1 and x M1. What is n M1? This is weight fraction of B in the mixture. And x M1, you know, it is weight fraction of C in the mixture. So, x M1, you have the equation, you can find the value of x M1. Then you are going to locate x M1 on the y-axis. And then you are going to go to the line that connects points F and S. So, the x coordinate of this point, the point will be nothing but M1 and the x coordinate of this point will nothing but be, it will be n M1. What is n M1? It is weight fraction of B in the mixture. So, this is how you have to locate point M1. Now, mixture M1, it settles into raffinate and extract phases, which then will reach equilibrium, and therefore point M1, it also lies on a tie line, and for this tie line, the point M1, it also lies on a tie line. So, I have drawn the tie line that is passing through M1. Endpoints of this tie line, they will represent raffinate and extract phases. So, we have points R1 and E1. So, this point on the A reach side of the curve, it will be representing R1, the raffinate phase, and a point on the B reach side, part of the curve, point E1 will be located, and E1 will be representing the extract phase. So, this is how you have or you can follow single stage liquid extraction operation on a ternary equilibrium diagram on rectangular coordinates. So, let us continue further. Then after you draw the tie line that passes through M1 and the endpoints of that tie line, they are going to give us X1 and Y1, and we have to use these two values to get the quantities of extract and raffinate phases that are found. So, the next discussion is we are going to understand how to calculate quantities of the two phases, extract and raffinate phases. The weight fraction of C in the raffinate is X1, as I told you. So, That means the y-coordinate of point R1 on the equilibrium diagram is x1. Whereas the weight fraction of C in the exact page is y1. Now, what is the meaning? The meaning is y-coordinate of the point E1, which I just showed to you in our previous discussion. So, y-coordinate of point E1 will give us y1. So, we need to plot the tie line that passes through M1. You need to mark the endpoints of that tie line as R1 and E1. R1 represents the raffinate phase, E1 represents the extract phase. Y coordinate of the point R1 will be nothing but x1 and y coordinate of the point E1 will be nothing but y1. Okay, so I am showing over here. So we have this point R1. So the y coordinate of this point will be was x1 and you have this point. Y coordinate of this point E1, it will give us y1. In short, we need to know the values of x1 and y1 in order to calculate E1 and R1, in order to calculate E1 and R1, quantities of E1 or quantities of raffinate and extract phases that are produced. Now equation 3, which was obtained previously, what is that equation? R1 plus E1 is equal to M1 and equation 4 is Fxf plus S1 into Ys, that is equal to M1 into Xm1, that is equal to E1 into Y1 plus R1 into X1. So we had obtained this equation earlier and we had called that as equation number 4, and then I can write this equation E1 Y1 plus R1 X1, that is equal to M1 into Xm1, and I am calling this as equation number 6. So when you know X1 and Y1 in equation number 3 and equation number 6, in equation number 3 and equation number 6, there are only two unknowns. Which are those two unknowns? E1 and R1. In equation number 6 and in equation number 3, E1 and R1 are quantities of the raffinate and extract phases. E1 is quantity of raffinate phase, E1 is quantity of extract phase and R1 is quantity of raffinate phase. So you have two equations, equation 3 and equation 6. You can solve them simultaneously and get the value of E1 and R1. So in this way, you can calculate the quantities of extract and raffinate phases. But the point is, in order to do it, you need to know the value of x1 and y1. How are you going to get these values? You are going to get these values by using the diagram, by using the tie line that you have drawn through the point N. So I hope the calculations are clear to you. If you have any doubts, so please mention them in the comment section. Then another concept that we will understand in this discussion, we will know how to find out minimum amount of solvent that is required. So for that, we will take the help of the equilibrium diagram which we had just drawn. Now M1, since mixture should separate into two insoluble phases, this point M1 should always lie beneath the binodal solubility curve in the heterogeneous region. You must remember the region below the binodal solubility curve, it is a heterogeneous region. What is the meaning of that? Every point beneath the binodal solubility curve, it represents two phases, two liquid phases. And point M1, since it will alternately separate into two phases, it must lie beneath the curve, and that too on the line Fs, because the mixture is produced by mixing F and solvent. So M1, it will lie below the curve and it will also lie on the line Fs. We have understood that. Now, let us understand one limiting case. What is the limiting case? M1 is located at R1 minimum. Where is R1 minimum? It is over here. So R1 minimum. The limiting case comes into picture when point M1 is located at R1 minimum at this point. So this corresponds to minimum amount of solvent that can be used, and it also corresponds to infinitesimal amount of extract that is formed at the point E1 minimum. So if I draw a tie line, the end point of this tie line will give me this point E1 minimum. So an infinitesimal amount of extract phase will be represented by that dash, by the point E1 minimum. Now equation 5, we have got equation for xm1. xm1 is fxf plus s1ys divided by f plus s1. And how to get xm1? We know xm1 is this thing. Okay. Now I will be finding that value of xm1 which corresponds to this point R1 minimum. So the y coordinate will be nothing but xm1, and I am calling it as max, xm1 max, because we are going to use that for finding minimum amount of solvent. So the point is, if I replace xm1 in this equation with xm1 max, S1 will be the minimum solvent that is being used. So xm1 max, if it is used in the equation will be transformed to this form: fxf plus S minimum into Ys plus F plus S minimum. In that case, we are going to get the minimum amount of solving after solving this. Next, we'll solve that. So we have just got equation for xm1. xm1 max is equal to fxf plus S minimum into Ys divided by F plus S minimum. So let us simplify it. So xm1 max, if I bring this term to this side, it will be xm1 max into F plus S minimum. That is equal to fxf plus S minimum into Ys. Let us solve the bracket. So it will be xm1 max into F plus xm1 max into S minimum. That is equal to F into xf plus S minimum into Ys. Then we will collect all F terms on one side and all S minimum terms on the other side. So it will be xm1 max into F minus F into xf. So F into xf is brought on this side. That is equal to S minimum into Ys minus xm1 max into S minimum. And on this side you can take F common. So it will be xm1 max minus xf into F. That is equal to Ys minus xm1 max into S minimum. So that is F upon S minimum will be equal to Ys minus xm1 max divided by xm1 max minus xf. So this equation can be used to find out the minimum amount of solvent. Then we have the concept of maximum amount of solvent. So let us understand. Again, we are going to use the equilibrium diagram that we have just drawn. So M1, as we understood earlier, it must be located beneath the binodal solubility curve on the line Fs. And now let us discuss the other limiting case. What is the other limiting case? The limiting case is M1 is located at E1 max. So where is E1 max? E1 max is over here. So earlier we discussed the case when M1 was located at this point. Now we are discussing a case when M1 is located at E1 max. So this corresponds to maximum amount of solvent that you can use, and it also corresponds to infinitesimal amount of raffinate that is formed at a point R1 max. And where is R1 max? R1 max is over here. R1 max. And the y coordinates of y coordinate of R1 max will be giving me a value, and I'm calling that value as x1 minimum. So we will be using x1 minimum to get the maximum amount of solvent that can be used. So for that, again, you have equation 5. So it is xm1 is equal to fxf plus s1ys divided by f plus s1. And now if I replace xm1 with xm1 minimum, I will have to replace x1 with xmax. So xm1 minimum, that is equal to f into xf plus smax into ys divided by f plus max. And you can solve it to get an equation for S max. So let us do that. So we have got equation for xm1 minimum, which is fxf plus S max into ys divided by f plus x max. So I'll simplify it. xm1 minimum into f plus x max is equal to fxf plus S max into ys. And let us simplify it further. Sm1 minimum into f plus xm1 minimum into S max, that is equal to fxf plus S max into ys. Then we'll collect all f terms on one side, all terms containing f on one side, and all terms containing S max on the other side. So this will be xm1 minimum into f minus fxm, that is equal to S max into ys minus xm1 minimum into S max. Then you can take f common, so it will be xm1 minimum minus xf into f, that is equal to ys minus xm1 minimum into S max. So that is we get f by xms, f by S max, that is equal to ys minus xm1 minimum divided by xm1 minimum minus ys, and you can use this equation to find out the maximum amount of solvent that can be used. So with this, I end my discussion for this video lecture. Here we have understood how to write material balance for single stage liquid extraction, then how to write balance for the solute, then how to follow these material balances on equilibrium diagrams, the equilateral triangular coordinates and rectangular coordinates, and then how to find out minimum amount of solvent that you can use, and then also how to find maximum amount of solvent that can be used in the operation. So with this, I will stop for today. I hope you have understood the concepts. So again, thanks for watching. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my channel. In coming few videos, I'll be talking more about stage-wise liquid extraction. I'll be solving some numericals where you are going to learn a lot of things. So I'm sure you'll be with me in my next video lecture. For now, thank you. Have a nice day and hope to see you soon in my next video.